It's 6 p.m. I will start the session after maybe 5 or 10 minutes. I'll wait till people join. Hi Siddhi, I'm waiting for few minutes. I will let people join and then we will start. Okay, I think we can start. So, welcome to the week 1 live session for the course Sensor Technologies, Physics, Fabrication and Circuits. Uh, Please confirm if I am audible to you. You can unmute yourself or write it in the chat box. I am audible to you, right? Okay, thank you. So let me introduce myself first. I am Ananya. I'm a PhD scholar in the Department of Electrical Engineering, IIT Kanpur, and I will be the TA for this session. So in every week we will have 2 live sessions. I will take one of these, and here in this session we will discuss some of the problems. So the idea for this live sessions are that we will solve problems. Those will be helpful in solving the assignments. So this will be mainly tutorial, not the theory part. I I hope that you have gone through the lecture videos. So uh, so here in this week, so the lecture videos covered the concepts of sensors. What is the concept? Okay, so the topics those were covered. The definition of sensor, transducers, and the difference between these, and a few terminologies which are related to sensors. Okay, that those describes the characteristics of a sensor, like how good or bad a sensor is, or whether the sensor will be applicable to our need or not, like whether we can use the sensor for the application we want to use, that will be useful or not. Okay, so I hope that you have gone through the lecture videos, and we will discuss some of the problems related to those videos. And I will be in the presentation mode most of the time, so if you have any doubt, you can unmute yourself and speak, or you can write it in the chat box also. I will check in the in between. Okay, so I'll give you the questions first and wait for a few minutes maybe, so that you can answer those, and we can discuss after each question. So let me give you the first question. So question 1 is, which of the following sentences are false? So first statement is, sensor technology may require a multidisciplinary approach. Next statement is, sensor always need a electronic system to function and convey information. Third statement is, sensors always need an embedded power source to work. Last statement is, sensor response must be predictive and selective to target parameter to give any useful information. So this is the question. Four statements are given, which is or are of these sentences are false. So you can give me the answer in the chat box, or you can unmute yourself and tell me the answer. I will wait for a couple of minutes so that you can write in the chat box. There may be multiple sentences which may be false. Two and three, okay. Okay, so I will explain this with the help of an example. So what is the first statement? Sensor technology may require a multidisciplinary approach, which is true. Okay. So how it is true? So like you all know about type of sensor which are used for biomedical applications, right? Which are used to sense some biological molecule or material. So suppose we want to detect a particular antigen, and for that we need to know that like how it reacts with the particular antibody. Okay, so maybe this is like an antibody. Okay, there is like space here, and it is an antibody, right? And it detects some particular antigen. So this is an example of, say, biomedical sensor. Okay. So to realize this type of sensor, you need to know the like chemistry and the biology behind it. Okay. So suppose due to this reaction, the binding of antigen and antibody, that leads to change in some parameter of the sensor. Maybe like this results, say, change in conductivity, maybe refractive index, depending on the type of the sensor, or any other parameter. Okay. So you need to know you should have the knowledge of this biological reaction and also about the these parameters like conductivity, refractivity, refractive index, and in most of the cases sensors are electronic in nature, so you need to have the knowledge of electronic circuits, like conversion of analog signal to digital signal. So that is why sensor technology is a it requires multidisciplinary approach. Okay. So first, this is true, right? Next statement is sensor always need an electronic system to function and convey information. So the sensor may not be electronic in nature all the time. It can be optical, it can be of other type also. One very common example of optical sensor is lateral flow immunoassay, if you are aware of that. So in this type of sensor, you might have seen this type of sensor. So there is one line, and if there is another line, red line, so you might have seen this type of sensor during COVID, like to test whether it is a COVID positive or negative case. So this line, it will always show as like red. So this is the control line, and this can be the test line. If this line is present, then it is like a positive case. If this line is not present, then it is a negative case. So this type of sensor you are aware of. There is no electronic system associated with this. Just by looking at the color of these lines, like whether these lines are present or not, we can say that like we can measure some parameter, whatever we are trying to measure, whether it is present or not. We may not be able to quantify exactly, but whether it is present or not, that we can decide based on that. So this statement is false. Next statement is sensors always need an embedded power source to work, okay, which is also false. I've just explained about the concept of lateral flow immunoassay. So there is no need of any power source. Okay, so just by looking at the lines, we can say whether it is a positive case or negative case. So there is no need of any power system associated with this. But most of the sensors need a power system, but not always. Next is sensor response must be predictive and selective to target parameter to give any useful information. So this statement is true. So we use a sensor to measure something. So the response must be predictive. So for that we do calibration of the sensor. So how we do calibration? We give some input, we take the output, and maybe like then we fit a graph, and then we explain this graph using like this curve using some equation, and this is how we do the calibration of the sensor. And next time when we measure some output, the corresponding input we determine based on this calibration curve. So the sensor response must be predictive. We should load this graph so that for this kind of output we can expect this is the input. Okay, and it should be selective to target parameter to give any useful information. Say you are designing a gas sensor. Suppose a gas sensor you are designing. And you are designing the sensor for a particular type of gas, say carbon dioxide sensor, and this is your sensor. Input is carbon dioxide and output is some voltage. Okay, and this based on the amplitude of this voltage, you can determine what is the concentration of this carbon dioxide gas. Okay, Now your sensors should be selective, so that if instead of carbon dioxide, if the input is some other gas, say nitrogen dioxide, the voltage should not change, or the change in voltage should be negligible compared to the change in voltage that corresponds to the concentration of carbon dioxide gas. Okay, so this is a very important parameters for sensor, that your sensor should be selective. So suppose this kind of sensors you will be used in many applications, maybe in industrial application. If the sensors are not selective, then if the sensor is used for some security purposes, then there will be like fault, that the security system will be faulty. Okay. So this is the first question. I hope it is clear. So I will go to the next question. Before that, before that, so I am using this meeting link. This has been shared with you. So if this meeting link does not work after 1 hour, if the call gets disconnected, then I have created another meeting link. I have already shared in the chat box. Please remind me to share it again, maybe after 40-45 minutes. If this meeting gets disconnected, then please use that link. Otherwise we will stay in the same link. Okay. Let me write down the next question. For a sensor, which of the below signal can be used to have a readable format in the system output? Option A is optical, B mechanical, C is electrical signal, all of the above. So what is the answer? Again, you can write in the chat box. Option D, all of the above. Yes. So the question was, uh, like, what is the readable format of a sensor output? So the options were optical, mechanical, electrical, or all of the above. So optical signal that can be an output of a sensor. I have already explained, like the color of, excuse me. An optical signal can be an output of a sensor. Optical signal. So what can be this signal? Maybe the color of the line, in case of lateral flow immunoassay, I'm using the short form, or it can be in terms of LED. Like maybe it is binary, on or off, or it can be color coded. Or anything, like it depends on the requirement. Okay, and mechanical signal can be an also output of a sensor. What can be a mechanical signal? Maybe a pendulum. So you can design maybe a sensor with a mechanical signal as output, where the like amplitude of the oscillations of a pendulum, that signifies some output. Based on that, you can say that the input may be this. Okay. An electrical signal, of course, most of the signals, most of the sensor have output as electrical signal. Right. And electrical signal can be voltage, current. So why most of the signals, most of the sensor outputs are electrical signals? So using an electrical signal as a sensor output, we can very easily, like, so the sensor outputs are in general analog in nature. So using an electrical signal which is analog in nature, we can easily convert it into a digital signal using a analog to digital converter. Okay. So which is useful in many situations, like there are sensors, maybe like the output of the sensor is, say, voltage, some analog voltage. So the voltage ranges may vary from 0 to 5 volt. It can take any value depending on the like measurement system you are using, the minimum resolution of the system that you are using for measurement. It can basically have any value between 0 to 5, but it will show some like value that the measurement system can like measure. Okay. Now for example, if you are measuring some signal and you are getting output as a voltage between 0 to 5 volt, now the output, say it is 2.7 volt. So this output, this number may not be useful for a common user. Okay, so what you want to do, instead of a like analog signal as an output, you want to interpret it using a digital signal. So you are converting this 0 to 5 volt analog signal using an ADC, analog to digital converter, to a digital value of say 0 to 1023. Okay, so it is like a 10 bit kind of digital conversion. Now, there can be a manual for the common readers. Say if the output range is between 0 to say 255, then do this. Okay, so this is say work 1. If the range is between 256 to say 512, then you should do this work 2, something like that. Okay, so you can write a code, like a very simple code, to like display a message that this works need to be done based on this sensor output. Okay, so this is why these electrical signals are used most of the time, so that like we can make a whole system out of the we can make a system out of the sensor. Okay, okay, I'll go to the next question. In the meantime, if you have any question, you can write it in the chat box. I'm also recording the sessions. I want to let you know that I'm recording the session, but please feel free to unmute yourself if you want to speak something. Question 3. Which of the following can be considered as a sensor? Option A is light emitting diode. LED. Option B is amplifier. Option C is thermistor. Option D is piezoelectric material. Again, I will wait for a minute or so that you can write in the chat box. Please write the correct answer.
Dad.
C, thermistor. Yes. Okay. Someone is Okay, so the option is C. So do you guys know about thermistor? I think it will be covered in the next sessions. So I will briefly tell you about this. So here other options are not correct. Light emitting diode is not a sensor. It can be used along with a sensor to make the output of the sensor readable, okay, readable for common user. Then an amplifier is also not a sensor. It can be used along with a sensor to make a system out of it. A thermistor is a sensor. A piezoelectric material, the material itself is not a sensor. It can be used to make a sensor. Okay. The correct option is thermistor. Answer is C. So if you don't know about thermistors, these are made up of semiconductor material. Okay. And they have negative temperature coefficient, NTC. That means as the temperature increases, resistance of this material decreases. Okay. So this is the typical behavior of a semiconductor material, and we can correlate the temperature increase to resistance decrease, and then we can measure the resistance very easily, and so that is how we can measure the temperature. Okay, the resistance can be converted to equivalent voltage. So by measuring the voltage, we can determine the input temperature. Now other materials are also can be used. So instead of a semiconductor material, if it is a metal, say, so the resistance in metal increases as the temperature increases, but that is like a different type of sensor. In thermistors, semiconductor materials are used. And what is the difference between thermistor and the sensors which use like metals? Those I think will be covered in in the later sessions, in later weeks. Okay, so we have different types of temperature sensor. Based on our requirement, we will use one of these. Say for example, if you want to measure a very high temperature, that's 1000 degrees Celsius, then one sensor may not work. And then say suppose you want not very you don't want to measure a very high temperature, say you want to measure only 150 or 120 degrees Celsius, but you need to measure it very precisely, like very accurately, because it is very sensitive, you need to measure it very precisely, so that the output of the sensor will be fed to some other system, and it is doing some critical work, say especially maybe in biomedical applications. Say the sensor output should be very precise. Okay, so based on our requirement, we will have different sensors. Okay, is there any thing that you will get the recordings? Yes. It will be shared later. I don't know when. NPTEL team will let you know. Okay. So thermistor is a sensor, and I will give you the equation that is related to a thermistor. So the resistance at a particular temperature T is R naught. Some reference temperature is exponentially dependent to some, this is the temperature coefficient, 1 by T minus 1 by T naught. Okay, so these concepts will be discussed later. I am just giving you an overview. So if it is not discussed in the session, we can discuss in the live sessions later. Okay. Next, as I mentioned, the piezoelectric material cannot be a sensor itself, but the material can be used to make sensors. So what are piezoelectric material? In piezoelectric material, electric charge is generated when external stress is applied. So you can make a piezoelectric sensor to measure stress, but you have to somehow measure the electric charge, the change in the electrical property in the material due to stress, and then you have to show it in a readable format. So the basic definition of a sensor is that the output should be in readable format. So simply using a material, we cannot say that it is a sensor. We have to make it the output in a readable format. Okay, that is why this option D is not correct. So this is the correct answer. Okay, I'll go to the next question. Which of the below substrates is better suited for a flexible sensor application when higher thermal processes are involved? The options are A, polyethylene let me write it first. So it is PET. So these are like plastic sheet, flexible. Okay, and B is PVC. So that is polyvinyl chloride. C is polyamide. And D is polyester. All of these are flexible material, but which one of these is suitable for sensor application when higher thermal processes are involved? So this is the question. Again, I will wait for a couple of minutes and please answer in the chat box. Option C, polyamide. Yes. Okay, so the answers are correct. It is polyamide. As I mentioned, all of these are flexible substrate, but the maximum temperatures these substrates can handle that varies. So the temperature range for a PET is approximately 130 degrees Celsius. Okay. So I'm giving you just a number. The exact number may vary, but like it is in the range. So this is around 130 degrees Celsius, and the temperature range for second substrate is PVC, is around 60 degrees Celsius. For polyamide it will be around 300 degree Celsius, and for polyester it is around 140 degree. Again, these numbers are approximate, but polyamide can handle higher temperature, okay, around 300 degree Celsius. So if you are aware of a substrate called Captain, this is basically polyamide. So the composition may vary. All of these are polymer material. Most of the like flexible substrates are polymer material. So Captain is one such flexible substrate. I have also used this one, and the substrate can sustain at a higher temperature. It can go up to 300 degrees Celsius. If like other substrate will melt, or the composition will change, but it can work up to 300 degrees Celsius, and the substrate is often used for space applications, if you are aware of. So this is one substrate you should keep in mind if you are designing a sensor that will be used for high temperature, in a setup where high temperature like the environment is it will go higher temperature, or after designing the sensor, like if you need other steps, maybe to make a contact, maybe to make the whole system, if those fabrication steps need higher temperature, then also you should use a substrate which can sustain higher temperature. So this is one substrate you can use in your design if you are designing a sensor. So that is for high temperature measurement. Let me share the second link. So this is the second meeting link. Use this link only if this meeting gets end after 1 hour. Otherwise we will stay in this meeting. Let's go to the next question. A temperature sensor is used to measure the temperature of boiling water. What is the temperature at which water boils? That is 100 degrees Celsius. So we want to measure 100 degrees Celsius basically. But our sensor is not 100% accurate and precise maybe, so it shows different reading. Okay. So the readings during the 5 measurements are 98.95 degrees Celsius, 101.05 degrees Celsius, 100 degrees Celsius, 99 and 101 degrees Celsius. So the question is, how accurate the measurements are. The options are 98.95%. Option B is 1.05%. C is 100%. D is 99%. And option E is 1%. Please calculate this and write the correct answer in the chat box. Okay. So why the answer is 100% even though the measurement readings are different? This is not exactly 100 degrees Celsius, but why the accuracy is 100%? So when in this case our input is 100 degrees Celsius, right? And we are taking 5 measurements, but we are actually measuring this 100 degrees Celsius. So what will be our output, how we take the output in this case, even though we are taking 5 measurements, but our input is constant. So what we will do, we will take the average. So what will be the average? 98.95 plus 101.05 plus 100 plus 99 plus 101. Divided by 5. There are total 5 measurements, and this will come out as 100 degrees Celsius. Others can calculate it. So our output is 100 degrees Celsius. So our input and output are same. So the accuracy is 100%, or we can say inaccuracy. That is 0%. However, even though our sensor accuracy of our sensor is very high, it is not very precise. Okay, so the output varies between 101.05 to 98.95. Okay, so this difference is basically so this difference is not precision, so the opposite of precision. So our sensor has this range, so this is the delta T range. So you can say that our sensor is not 100% precise. I will go to the next question. Let me ask you one thing, so you have registered for the examination for this course. How many of you have registers? You can raise your hand or maybe write. Okay, I think no one has registered, but please check the assignment due dates and can submit it before the deadline. Let me go to the next question. Two temperature sensors T1 and T2 are used to measure the temperature of boiling water five times. The readings are for T1 sensor, it is 96.5 degrees Celsius, 101.5 degrees Celsius, 100 degrees Celsius, 99.8 degrees Celsius, and 96 degrees Celsius. For the second sensor, it is 97.5 degrees Celsius, 98.5 degrees Celsius, 100.5 degrees Celsius, 99.95 degrees Celsius, and 99.1 degrees Celsius. The question is, which sensor is more precise and which one is more accurate? So this is the sensor. There are two sensors measuring the same temperature of boiling water, which is 100 degrees Celsius, and these are the readings for 5 measurements. Which one is more precise and which one is more accurate? So this the terms accuracy and precision, these two terms were discussed in the lecture videos, but since it is a numerical problem, I will briefly explain like what is accuracy and what is precision, so that you can solve this. Okay, so what is accuracy? Accuracy means the correctness of any like system, and typically we want a highly accurate sensor. So what accuracy means, the correctness of a sensor. Say if this is our calibration curve, this is input, this is output. Say we have a linear calibration curve, and so this is the calibration curve. So we already know that the input output relation is linear. Okay, and this is our sensor output. See, now as this is our calibration curve, say this is the voltage value. So as per this output, this voltage range, our input is this temperature. Okay, so this is our output, but actually our input is T2. Okay, this is the actual input, and this is the output we are getting due to measurement error. Okay, measurement error or the error of the system or the sensor, and this is the inaccuracy. Okay, and opposite of inaccuracy is accuracy. Now what is precision? Precision is how narrow the distribution of measurements are. Okay, it signifies. So what it means, suppose we are measuring 100 degrees Celsius and we are measuring it multiple
Oh,
times.
1 second, show the mark.
Sorry, I could not hear.
Show the question mark.
T2 is more. Your voice is not clearly audible to me. Maybe you can write. T2 is
Ma'am,
more.
please show the question, ma'am.
Okay, question. Okay. Okay, so this is the question. You can try to calculate and tell me the answer. I will wait for a couple of minutes, okay, so that you can answer. And you can mention in the chat the accuracy in percentage also, and the precision and the distribution for precision, that is the delta t range also. Suppose T1 is more accurate, what is the percentage of accuracy? And if T2 is more precise, then what is the delta T value? What is the distribution? I am also calculating along with you. So this is for the first sensor T1, and for T2 similar calculation. something? So these are the comparison for T1 and T2. So the accuracy is high for T2 and also precision is also high for T2. So our sensor T2 is more accurate and more precise. Okay. I hope you also got the same values, like same numbers. If I have made any calculation mistake, then you can correct. But you got the idea how to do this calculation. Okay. Vivek, I will provide the slides. It will be available to you. NPTL team will share all the details with you. Okay. Previous slide. Okay. T2 is more accurate, so I hope you will also was able to calculate it. Okay. So I'll go to the next question. So the question is, which of the characteristics of a sensor would require less complicated electronic readout circuit? So the options are parabolic calibration curve, option B is exponential calibration curve, option C is linear calibration curve, and last option is all of the above. think about it, and you can tell me the answer in the chat box. uh, don't simply just give the answer just by looking at the options. Please try to find out the reason, like why it is simpler to make this calibration curve. Okay. Linear calibration curve, yes. But why a linear calibration curve is easier to implement?
Since it is linear, we may have a less number of variations, and when we are trying to find out, like it will be easier to calculate when compared to the other curves, which will have more ups and downs. Like the changes are more there when compared to the linear calibration curve.
Yes, so what you are saying is correct. More in a technical term, I will write it here. So the equation of a line is some y equal to mx plus c. So here x is your input and y is your output, right? Here you have two variables, m and x. So in a linear calibration curve, if the relation between input and output is linear, then you have to determine these two variables. Okay. Now if it is in some other form, like if it is a parabolic, then it may have a form like ax square plus bx plus c. Then you have more number of variables, a, b and c. The more complicated the input output relation, you will have more number of variables or more number of constants to determine. Okay. And it is always easy, like ultimately you have to interpret these constants using some circuitry, right? Less number of constants means less complicated circuitry. Okay. Another reason is that suppose your relation is exponential. Say this is your input and this is your output, and it varies exponentially. So within a very small range of input, the variation of output is very high. Okay. So you have to measure the inputs and outputs very precisely, so that for a small variation of input you will get a large variation in the output, but there may be a chance of error. Say this is your I think it will be opposite other way around. If So if this is the input and this is output, this kind of relation. So this is our input 2 and this is input 1, say. Okay. So the chances of error for this measurement, because the measurement system you are using may not be able to measure this output 1 and output 2 very precisely. Okay. Suppose you are measuring voltage and the resolution of the voltmeter there you are using is say 0.5 volt. I mean it's very high, but I'm saying hypothetically, and this variation is say 0.2 volt. So you will not be exactly determined whether it is input 1 or whether it is input 2. If it is a linear curve, so like you exactly know the input output relation, and it will be easier to implement, and in many cases it will be easier for measurement system also, based on the resolution of the system. So less number of parameters is always easy to implement. That is why we go for linear calibration curve. Okay. So suppose you know the capacitance is epsilon A by D, right? So you are measuring some input parameter because of which the capacitance of your device, of your sensor is changing, say. Now you can measure the capacitance, like change in capacitance delta C can be due to delta A, change in the area, or it can be due to delta D, the distance between this is the relation for a parallel plate capacitor. Okay. So if this is some say this is one plate, this is one plate, you can either vary the area of cross section due to this movement of this one electrode, or you can change the distance, right? Now you can see here the distance is inversely proportional and area is directly proportional. So it is always easier, it will be always easier to make a sensor if you make the input parameter as the change in the area of this kind of sensor. So you will be able, you will appreciate it more as the course will go, we will learn about different types of sensor. I just want to tell you that if there is a directly proportional kind of relation, then it is very easier to implement. Okay. I think capacitive sensors will be covered in one of the weeks, then you will learn about it more. So this is the next question. I have taken it from previous assignment. So a calibration graph is given here. So the input here is, so this is input. Input is concentration in millimolar for some maybe chemical solution, and the output is resistance in kilo ohm. So this is the output. Okay. So this is the calibration curve given, and the question is for analyte concentration of 50 millimolar, the resistance is 3 kilo ohm, and for 400 millimolar it is 11 kilo ohm. What is the sensitivity of the sensor? So this is the question. Give it a try and write the answer in the chat box. we calculated. Answer is A, option A. Okay. So maybe it was discussed in the last class. Actually, the reason is that there are two sessions because the number of students registered for the course, a large number of students have registered. So that is why there are two live discussion sessions, and the questions may not be exactly same in both the sessions because two different EAs will take. But people can, the idea is that people can join as per their convenience. So we, the sessions were kept at either on weekends or on not on during office times, okay. Because the audience, we don't know exactly the audience, so that is why. Okay, so let me explain. So what is the sensitivity of a sensor? Sensitivity of a sensor is change in the output, incremental change in the output to incremental change in the input. Okay, so this is the definition of sensitivity of a sensor. So the unit of sensitivity can be whatever the unit of, it depends on the unit of the input and output. Okay, so what is given? For 50 millimolar, the corresponding output is 3 kilo ohm, and for 400 millimolar, the corresponding output is 11 kilo ohm. So our sensitivity will be 400 minus 50. No, so this should be the output. Okay, 11 minus 3 by 400 minus 50, and the unit will be kilo ohm per millimolar. Okay. 11 minus 3, 400 minus 50, so this will be 0.228 kilo ohm per millimolar. So the answer is this. So this is one important parameters of a sensor. So we typically want a highly sensitive sensor so that it can give high output value for a small change in input, but we also want the sensor to be selective so that it gives higher output value for a particular sensor or the particular analyte we are targeting. Okay. So here the calibration curve is linear, but you can see that the calibration curve is linear for a particular range of input. So as I mentioned in the last question that we prefer a linear calibration curve. What that means is that we want a linear calibration curve in the input range of our interest. So maybe the input output relation is not linear, but if we don't want that range, we are not going to use that range. Even if that range are not linear, then we don't consider it. Okay, we typically want the range in which we will be operating the sensor that to be linear. Okay. So in many cases, if the input range is limited, if the input range is very small, even though the relation between input and output is not linear, but in that range we can use a linear approximation, piecewise linear approximation kind of approach, and that will do. Like most of the sensor we use in practical scenario. So when you are designing a sensor, you should consider those situations. For example, if you are designing a sensor that needs to be operated in a very different environmental conditions, maybe at a temperature, say you want to use the sensor in Kashmir as well as in some like in some areas of Rajasthan also, the temperature variation will be very large. So you want the sensor to give similar output. So you should consider those parameters so that the sensor will give like similar results in both of these conditions while maintaining the other criteria like the selectivity, sensitivity, and rest of those. I think the answer is, so you should have corrected me, the answer is A. I hope it is clear. Okay, so I will try to give few more different questions in the live sessions, okay, so that the sessions will be useful. But you can join as per your convenience, like whichever timing is best suited for you, or you can join both of the sessions, it depends on you. And these sessions are for so that you can solve the assignment questions easily. So if you have any doubts, because the rest of the lectures are already recorded, so if you have any doubt you can ask, and if I can't give you the answer right away, then I will note it down, and at the end we will have a doubt clearing session maybe if you need. Then I will explain those questions also before the exam. So let's go to the next question. This is again the same calibration curve. So here the question is, what is the sensitivity of the sensor at 450 millimolar concentration from the calibration curve? Okay, and give me the answer. Here the sensitivity is being asked only at a particular point of input. So when it is asked at a particular point, we just take the slope at that point. Okay, so that is a hint. because I have discussed similar problem in one of the questions, so you can solve it in a similar way. So yeah, I think this is a similar question. So what will be the answer for this question? Okay, since there is no answer, let me answer this question. So here the sensitivity is asked at 450 millimole concentration. If you see this graph, input output
450
relation,
there is 0.
yes, it is 0. So this is 450, and here the input output relation is flat. So the slope is 0. That is why the sensitivity is also 0. Okay. I am writing this because I will upload the slides, okay, so that people can understand. So what is the range for this sensor? There is one term associated with sensor is range. It is the range in which we can operate the sensor. Okay.
to 400.
So it is 50 millimolar concentration to 400 millimolar concentration. Okay. For that range only, if there is a change in input, we will get a change in output. Otherwise, if the sensor is operating in this range, then we will not get a change in the output. So this is one term that is associated with sensor. This is the range for which a sensor can be used. Okay. The sensor can be operated from operated at say 450 millimolar, but it will not give the correct output. Or I can say that it will give same output for this range of input, so which is not very useful. Okay. So since I have some time, more time till 8, so I'll discuss one more concept. So this is one question that I want to explain. What do you understand by calibration of a sensor, and explain how it is done using an example. Okay. So what is calibration, that you have studied already. So I'll briefly say this. What is calibration? It is basically the relation between output and input. So if someone is on mute, if you want to say something or ask something, then you can ask, otherwise please mute yourself. Okay. So what is calibration? Calibration is basically we do to know the input output relation of a sensor. So why we need calibration? To know the input output relation of a sensor. Next question is how we do calibration. So we apply known input and measure the output. Okay. So what can be a known input? So we know that boiling point of water is 100 degrees Celsius. Suppose we are making a temperature sensor, and so the boiling water can be an input which is 100 degrees Celsius, and if we are measuring the output, it suppose it gives some voltage, then we will know that that voltage corresponds to 100 degrees Celsius. So how we do calibration? We give known input, we measure the output, there will be discrete data points, say, and then we try to fit these data points using some curve. Okay, so this will give us, so this is some equation of a curve. Okay, so this is the first thing we do when we get a sensor where the input output relation is not known, or if you are designing a sensor, and once this calibration curve is known, then we can measure any like input, and based on the output measurement we can determine what is the like input for that output value. Okay, so this is the first thing we do with a sensor, and it needs to be done like periodically. If you are using a sensor, we say in different conditions, at different temperatures, at different humidity, maybe at different environmental conditions, the calibration curve may vary, or the calibration curve may vary with time. So there may be some deterioration in the sensor, some deterioration of the material that is being used in the sensor. In that case also the calibration curve may vary with time. So this needs to be done. So if you remember, when we used to do like experiments in UZ level courses, we used to do calibration before starting an experiment, so that with time, if there is a deviation or there is a error with the sensor, that we get to know, and we can correct our result, correct our values. Okay, now like I will explain it using an example. The example I am using, say, a strain sensor, a sensor that is being used to measure strain. So let's say suppose our sensor is of electrical type, so our output is say resistance and change in resistance. Okay, so output is resistance. And we can we can change this resistance to an equivalent voltage very easily. Okay, so this is an electronic sensor. Now what is the formula for resistance R, which is equal to rho L by A. Okay, L is the length, A is the area, right? You know this formula. Now if there is a change in this length, then the value of the resistance will change. Okay, now in case of strain sensor, how the resistance changes. So when force is applied, say, the length of the material will change, and we can measure that change in length, and that can be converted to equivalent stress or strain in the system. So I will write down the equation. The change in resistance is proportional to the length, and the relation is given by, so delta R by R is basically K dot epsilon. So here K is the Gauss factor, and epsilon is the strain. Okay, now you want to measure the strain, and for that you can measure the change in resistance, but we don't know the Gauss factor. So this is a material parameter that is unknown to us. We don't know the sensor, how the sensor is made, what material is being used. So even if we don't know the value of these parameters, these material parameters, to use a sensor we don't need to know these values. So what we do, we make a Western bridge circuit. If you I hope all of you remember Western bridge circuit. So we'll make a Western bridge circuit with some known resistance, say R. So this is R, this is R. Can be different value also, does not matter. And here we will put our sensor. Right? This is our sensor. Then we complete the circuit of a Western bridge. We will apply some voltage. Drawing is not very clean. I hope you got what I am saying. Okay. Now, if you remember, I'm not going to write down the equation for a Western bridge circuit, but how the measurement is done, you can check, or I hope you already remember it. So we will measure the change in this resistance. We will apply some force or strain to the sensor, and we will measure the corresponding voltage that is generated here, and based on that we will determine the resistance of the sensor. So our calibration curve will be like this. We will have, so this is our input, which will be some load or force, or the parameter in which form you are measuring. Okay, you are using the sensor, and our output will be like strain, okay, because it is proportional to delta R, change in the resistance value, okay. So even if you don't know this material parameters, you will be able to get the calibration curve for a particular load, for a particular input, what is the strain, okay. So this is like how the calibration of a sensor is done, okay. So you don't need to know the background for which the background which is used to make a sensor, and we just need to do a precise measurement with known input, okay. And this western based circuit, because most of our sensors are electronic in nature, so western like calibration using a western based circuit is very common. It is often used because in many times we actually convert the change in resistance to some equivalent voltage. This is all I wanted to discuss. Okay. Calibration curve, these topics were covered in this lectures. If you have any doubts, you can ask, or we can end the session. Okay, if there is no doubt, I think we can end the session. So I will take the sessions on Tuesdays, similar timing. It will be notified by the NPTEL team. If there is any change, then you will get notification prior to the session, okay. And I hope you find the session useful. If you have any doubts from the next session onward, you can ask. And thank you for joining the session. Thank you. So I'm going to end the session now, end the meeting.